Okay, let's look at two different scenarios. One where the gas is changing and one where the gas is not. But what do I mean by the gas is changing? I'm talking specifically about the conditions. So when you release a balloon, a helium balloon at ground level, it doesn't pop right away. It floats up pretty high. But at a certain point, as the air pressure decreases, the volume of the balloon has to increase to compensate, and eventually the balloon will pop. This is kind of what scenario one is similar to. A sample of oxygen gas occupies a volume, an initial volume of 1.25 liters at 273 Kelvin. If the pressure remains constant, what is the new temperature of the gas if the volume decreases to 0.25 liters? So this is a problem where the conditions change. We don't want to use PV equals nRT for situations where the conditions of the gas change. Maybe we'll use the combined gas law if there are more than two conditions that change, but really, we just want to choose one of the four different gas laws that we learned about this unit. Now, maybe you don't remember the gas laws. You're like, I don't want to memorize all four different gas laws. And to that I say, that's okay. All right? We could still reference PV equals nRT. Now let's look at what's changing in this problem. I color-coded it for you, and I think that when you are given these types of problems, it's really important to either give yourself a note or some type of indication as to what is exactly changing here and what is constant. We're being told that pressure here is constant. There's no mention of moles. There's no mention of mass. So we can assume that pressure and moles are being held constant. R is just a constant. We don't need to use R here because we want to see how the conditions of this gas change. So we're only focusing really on volume and temperature. And if you know your gas laws, then you should know that this is actually Charles's gas law. V1 over T1 equals V2 over T2. All right? And if I was to set up this problem, what's V1? What's volume 1, or our initial volume? Told us our initial volume is 1.25 liters. And our initial temperature is 273 Kelvin. So we just have to set that equal to the new conditions that this sample of oxygen gas changes into. It looks like its volume decreases. I think a good indication that you're looking at a gas that is changing are words like increasing, decreasing, maybe even the word constant. You want something about the gas to be literally changing. And we're not given any clue as to what the new temperature is. In fact, the question actually asks what will be the new temperature. And the new temperature will be whatever we solve for, T2. That would be our answer. Now, scenario 2 is a little bit different because we don't have a gas that's changing. Let's read this. A scuba tank contains 5 moles of oxygen at 280 Kelvin with an internal pressure of 7.60 atmospheres. What is the volume of the tank? So nothing here is changing, but I think something that is interesting is that, we're given a new variable. We have 3 variables now. We have moles, we have pressure, and we have temperature. And the question is asking us for volume. So in these types of problems, you can just use PV equals nRT because nothing's changing, right? And if it really helps, document what you know. We know pressure, we know volume, and we know temperature. I'm sorry, we don't know volume. What am I talking about? We're trying to get volume. All right, this is our goal. We know moles. All right. So we know temperature, moles, and pressure, and we're solving for volume here. If I were to rearrange my equation in the small amount of space I gave myself here, you would get something like volume equals moles times R times T, temperature, all over pressure. I didn't write the exact values here, but you would just plug in directly what you got in the problem here. Another instant that you may be using the ideal gas law and not some scenario where the conditions are changing is gas stoichiometry. Very often in gas stoichiometry, you're given a reaction, and you're trying to figure out either maybe a final volume, maybe how many moles you needed to do a reaction. I mean, typically gas stoichiometry is used to go between volume and moles. But really you can go between any different variables. At the end of the day in gas stoichiometry, we want moles.